My name is Katie Olin. Today I'll be talking to all of you about how fire intensity affects the clonal regeneration in coastal redwoods. So as I'm sure all of you are aware, fire is an incredibly powerful disturbance. It is a huge player in shaping our Earth's ecosystems. It does everything from affecting atmospheric composition, nutrient cycling, and even the composition of our plant communities. And fire in California specifically is very frequent, so as you might assume, we have a lot of plants that have become specifically adapted to this frequent fire regime. For example, in chaparral communities, we see plants that sprout as a response to fire. We also have a lot of plants in California that are specifically reliant on fire for things like reproduction. For example, lodgepole pines have serotinous cones that only open after fires occur. And we see a lot of these same fire adaptations in our species of interest, coastal redwoods. So redwoods have this really thick insulating bark which protects their sensitive inner wood from fire. Also, being the tallest trees in the world, I think the tallest coastal redwood is about 380 feet tall, so the crown of the tree is very high, and as such, fires cannot often get up there, so their crowns are protected from fires most of the time. Also, their main form of regeneration is clonal. So a very low percentage of coastal redwoods are actually the result of a seed. Instead, most of them are clonal sprouts. So as you can see in this picture, we have a cut down tree in the middle and that ring of trees growing around it. So those are all genetically identical individuals. So what happens is that parent tree in the middle, which I'll continue to call that the original tree, a parent tree, and those trees that have come up sprout through burrows in that root mass. So they're all connected to that same root mass, originating from the tree in the middle. And all of those work together to give them a huge competitive advantage against other species in those communities. So they are the dominant species a lot of the time. And because they are the dominating species in communities where they're found, they are incredibly important, which is why they were our focus for this study. So we specifically were wondering if the intensity of fires that are going through these communities change the way that redwoods sprout. So based on the way other species respond to fire in similar ecosystems, we assumed that as fire severity increases, we would also see an increase in clonal reproduction happening in these trees. So our study was focused in Big Sur, very beautiful, great place to spend your time. So we focused on a 19-mile span along the Big Sur coast that encompassed 5 different sites which had experienced 4 different fires. So we had fires as recently as 2013, and fires ranging all the way back to 1985. Those fires were also of different levels of severity. So in 2013, it was a small roadside fire. But then in 2008, that was the Basin Complex fire, which affected thousands of acres along the Big Sur, in the Big Sur area. Overall, we were able to cover more than 60 miles of trail, so pretty diverse areas in this area. So for our sampling method, first we located parent trees that had rings of sprouts that were distinguishable from the sprouts coming up around other parent trees, so that we weren't confusing them as we were counting the clonal regenerates. Once we had found a good parent tree, we measured the size in 2 different ways. First, we measured the diameter at breast height, that's the DBH, just using a tape and wrapping it around the tree. As you can see in that picture, there's Mark, one of my research assistants and partners. And then we also measured the height of the tree. As I mentioned before, they're hundreds of feet tall, so it's kind of hard to measure the tree heights directly. So instead we used a laser rangefinder to estimate the heights. So because we were using a laser rangefinder, there was a little bit more error in those calculations. Once we had measured the size of the parent tree, we went ahead and moved on to fire severity. We measured that in 2 different ways. First, we measured the height of char along the main trunk of the parent tree. As you can see in this picture, it's a little dark, so it's hard to see here, but the charring on the tree is very distinct to uncharred. There we go. So you can see that black there is very distinct from the uncharred wood. So we measured the highest point where there was charring along the tree, and then we also measured fire severity as an ordinal measure. So we classified this in 4 different damage classes, ranging from no damage all the way to goosepen formation. So a tree with no damage would have been the lowest severity. The next most severe would have been a tree that only had charred bark, like we see here. Next, if the fire was able to burn through that insulating bark and expose the inner wood, that would have been the next most severe. And then finally, if the fire was able to burn through that sensitive inner wood and create a cavity called a goose pen, that would have been the most severe. Fun little aside, they're called goose pens because settlers used to actually hold geese and other livestock in the burned out cavities, just to give you a sense of how big these trees are. So then we moved on and we went ahead and counted the clonal stems for each of the parent trees. As you can see in this picture, that giant tree in the middle, that is the parent tree, and all that leafy green stuff at the bottom, those are all clonal stems. So we did that for each parent tree. Overall, we were able to sample 188 redwoods. Among those, we had 3 with no damage, 110 only showed charred bark, 38 in addition to charred bark had heartwood exposure, and then finally we had 37 that also had goose pen formation. Here's a first glance at our data. Along the y-axis here we have the bull char height. That's referring to the charring along the trunk of that parent tree, so that is our measure of fire severity. And then along the y-axis we have the total number of saplings. So as we look at fire severity versus sapling production, initially we do see a really strong statistically significant positive correlation between the two. So this was an indicator right off the bat that we had the right idea with our hypothesis, and yes, there probably is a positive correlation between fire severity and sapling production. Looking at our other measure of fire severity, you see that same correlation, really strong positive increase of sapling production as fire severity increases. Before we could assume that we were seeing an increase in sapling production just because the fires were more severe, we also looked at how sapling production was correlated to the size of the trees. The thought there being an older tree would probably be bigger, and older trees would also probably have more time to clonally reproduce. So using size of the tree as a proxy for age, we looked at the size versus sapling production. On the left we have the diameter, on the right we have that tree height. As you can see, diameter is also positively correlated to sapling production. There isn't that strong of a correlation between the height of the parent tree and sapling production, probably because of the error in that measurement. So to try and figure out, now that we have a confounding factor, now we have size or age affecting the number of saplings we see on parent trees, but we also have fire severity. So we did an analysis of covariance to try and pull out that confounding factor. So again, we have diameter along the x-axis, saplings along the y, and then those colorful lines are different damage classes, the fire severity. So that blue line along the bottom are trees that showed no signs of fire damage, and then that bright red line on top are the most severely damaged trees that had goose pen formation. So as you can see, even though overall there is an increase in sapling production in larger trees, we still see an increase due to severity. So for example, 2 trees with a diameter of 1 meter, a 1 meter diameter tree with no damage had far fewer saplings than a tree of 1 diameter with a goose pen formation. So we still see that strong jump due to fire severity, even as we pull out the confounding factor of size or age. So this was able to let us confirm our hypothesis that yes, fire severity is positively affecting the amount of clonal reproduction that redwoods are doing. So unfortunately, we weren't specifically able to look at what is causing this. We were just able to confirm that it is happening. We speculated that it's probably a response to light or a response to trauma. The thought process there being that as a fire comes through, it would clear out other debris and low-lying vegetation and allow the sprouts access to more light and other nutrients in the soil. It may also be a response to trauma. So if a fire is severe enough to burn a cavity through these giant trees, they may be more likely to divert their resources into reproducing in order to give them their best chance at persisting. So this has really important implications for how we manage our forests. In the past century, over the last century, the United States as a whole has had a total fire suppression policy as far as fires are concerned. Thankfully, that is starting to change. But as you can see, not only can these trees resist fires, but they actually benefit from them. So it is incredibly important for us to shift towards a more natural regime and let these fires burn. This also has important implications for our management of trees in the future. So as climate change changes the way different processes come through these communities, it's really affecting the way that different plants are able to persist and grow. So with different pressures due to climate change, we may be able to use fire to leverage the way that we help promote the growth of redwoods if they're being damaged by other things like this. Sorry. So I'd just like to give a quick thanks to Andrew Latimer, who's here in the back. He's my advisor. He's been awesome. Blake Settle, who couldn't make it today, and all of my team of undergraduates who helped me out in the field. Mark's here. They're amazing. Also the UCNRS class where I actually was able to start this project, and I kind of took it off on my own from there. So does anyone have any questions?
Out of all the places you've gone, like, did you see any differences in sprouting in certain locations?
So we actually, because I only had 15 minutes, I couldn't talk about it, but we did analyze them on a replicate basis.
Okay.
So comparing the different sites, there wasn't a really big difference based on the different locations. There was a little bit of differences based on the most recent fire that location had experienced, but they all still showed that same relationship, just on varying scales. Yeah.
Do you know how the morphology of the sprouts works? Like, do they already exist? Because you mentioned that maybe they're responding to light. Are they already there in the base of the redwood and they just come up at a certain time? Or do they only form once an incident occurs?
So that's a place for future research. We don't actually know the method that sparks the clonal sprouting. We just thought that if it was something that was constantly occurring, sprouts might be more likely to be able to persist after a fire.
Do you collect any data on tree density in the general areas you're working on?
No, it's pretty consistent. They're more likely to grow in different areas because they rely on fog. They're so tall. They get most of their they get a lot of their water from the fog belt instead of water in the ground. So they're more likely to be denser redwood stands in ravines. But as far as the stands of redwoods, the densities were pretty consistent. Yeah.
Did you guys use any methods to make sure you weren't, there was no biases in selecting trees that were burnt with more clonal sproutings already? Like when you selected the tree that was already burnt, wasn't there any?
So we sampled all trees that we were able to distinguish because we don't have the ability to actually do genetic tests to make sure that a stem that we're counting actually is genetically identical to the parent tree that we're attributing it to. We had to choose trees that were far enough apart to do that, but there wasn't a huge influence at all as far as fire intensities go. So no bias there.
How do you have any ideas on how you're going to move forward measuring like the effect of light or soil quality on the number of sprouts?
I haven't actually worked out methodology for that. That's just an interesting place I would like to look into that. There's not a lot of research on it right now. I hadn't thought about it. I was mostly focusing on this one.
Thank you so much.